Picture this. You're a Chinese merchant in 1520, and you need to move 200 tons of porcelain, silk, and spices across 2,000 miles of open ocean. The monsoons are unpredictable, pirates lurk in every strait, and one wrong storm could send your entire fortune to the bottom of the South China Sea. What do? You build a junk, not just any boat, a Ming dynasty engineering marvel that could survive getting slammed by typhoons, patched up with basic tools and still make it home with your cargo intact. Most people think junks were just those weird-looking boats with the funny sails you see in old paintings. Wrong. These vessels were floating fortresses of practical engineering that dominated Asian sea lanes for over 1,000 years, while European ships were still figuring out how to stop sinking every time they hit rough weather. Chinese shipwrights had already solved problems that wouldn't be addressed in Western shipbuilding until the 19th century. We're talking about watertight compartments, balanced rudders, and sail systems so efficient they could be handled by half the crew of a European ship. Here's what blew my mind when I started researching this. A single Ming junk could carry more cargo than 3 Spanish galleons, while requiring fewer sailors to operate. The largest treasure ships built for Admiral Zheng. His expeditions were reportedly over 400 feet long. That's bigger than Christopher Columbus's entire fleet combined. And they did it all with techniques that were considered trade secrets, passed down through generations of master shipbuilders who guarded their methods like state secrets. The real genius wasn't in making these ships big. It was in making them nearly indestructible. When a European ship took damage, you prayed you could make it to port before it sank. When a junk got hit, you sealed off the damaged compartment and kept sailing. It was like having a ship with built-in lifeboats, except the lifeboats were part of the ship itself. But here's the thing that really hooked me. Despite being one of the most successful ship designs in human history, most people today couldn't tell you the first thing about how these vessels were actually built. We know all about Viking longships and Spanish galleons, but the engineering secrets behind the ships that carried more cargo across more ocean than any other vessel, that knowledge was locked away in Chinese shipyards for centuries. That's exactly what we're about to unlock. Today, we're stepping inside a 16th century Ming shipyard to watch master craftsmen build one of these incredible vessels from the ground up. We'll see how they selected timber that could bend without breaking, created joints so tight they could hold back the ocean itself, and assembled everything using techniques so advanced they seem almost magical. And trust me, by the end of this, you'll understand why European sailors who first encountered these ships thought they were looking at floating cities rather than ordinary boats. Our journey starts in the timber yards of Longjiang, near present-day Nanjing, where the imperial shipyards operated like massive industrial complexes. Walking through these facilities in 1520 would have been like touring the world's most advanced manufacturing plant, except everything was powered by human muscle and centuries of accumulated knowledge. The first thing that would hit you is the smell, not the pleasant scent of fresh-cut wood you might expect, but a complex mixture of seasoning timber, boiling pitch, steaming bamboo, and the acrid smoke from the lacquer pots that never seemed to stop bubbling. The sound was equally overwhelming. The rhythmic thunk of adzes shaping hull timbers, the scraping of planes smoothing planks, and the constant hammering from the hardware forge, where iron fittings were being shaped by hand. The scale of these operations was staggering. A single large junk required timber from hundreds of trees, and the shipyard maintained seasoning stacks that looked like wooden mountains. These weren't random piles of lumber. Every piece was carefully selected, marked, and positioned according to when it would be needed in the construction process. The master builders could walk through these stacks and tell you exactly which timber would become the keel, which pieces were destined for the mast steps, and which planks would form the crucial watertight bulkheads. Here's where things get really interesting. The Chinese had figured out that different parts of a ship needed different types of wood. The keel and major structural elements were built from namu, an incredibly dense hardwood that could resist the constant flex and stress of ocean voyaging. The planking used teak when available, prized for its natural oils that repelled shipworms and resisted rot. Interior bulkheads often incorporated camphor wood, which not only provided strength, but also helped preserve the cargo with its natural insect-repelling properties. But getting the right wood was only half the battle. Every piece of timber had to be seasoned properly, and we're not talking about a few months of air drying. Major structural timbers were seasoned for 3 to 5 years, carefully stacked with spacers to allow air circulation while preventing warping. The Chinese had learned through centuries of trial and error that rushing this process would result in ships that literally fell apart at sea. The preparation work was where the real craftsmanship showed. Master carpenters would examine each timber like a doctor examining a patient, looking for the grain patterns that would indicate how the wood would behave under stress. They developed techniques for joining multiple pieces into single structural elements. The keel of a large junk might be built from 6 or 8 separate timbers, each one carefully scarfed and joined to create a backbone stronger than any single tree could provide. The hardware inventory tells its own story about the sophistication of these shipyards. Bronze fittings were preferred for underwater applications because they resisted corrosion better than iron, while iron was used for structural bolts and spikes, where strength mattered more than longevity. The amount of metal in a single large junk was enormous, tons of carefully forged fittings, each one custom-made for its specific location on the ship. Now comes the part that separates Ming shipbuilding from everything that came before: the revolutionary approach to hull construction. While European shipbuilders were still arguing about whether to build the frame first or the hull first, Chinese master builders had developed a hybrid system that combined the best of both approaches. The process started with what they called lofting, laying out the ship's lines full size on the ground near the building slip. This wasn't done with blueprints or detailed drawings. It was accomplished through a combination of traditional proportions, mathematical relationships, and the master builder's accumulated experience. The result looked like a giant geometric puzzle drawn in the dirt, but it contained all the information needed to build a vessel that would handle properly in every type of sea condition. The keel-laying ceremony was both practical and spiritual. The master builder would select the most perfect keel timbers, often pieces that had been seasoning for years while waiting for just the right project. These timbers were scarfed together using joints so complex they looked like 3-dimensional puzzles. The Chinese had developed dozens of different scarf joint patterns, each one designed for specific structural requirements. Some joints were designed to resist lengthwise tension, others to handle twisting forces, and the most sophisticated ones could handle multiple types of stress simultaneously. Setting the stem and stern post required equal precision. These weren't just attached to the keel, they were integrated into it through carefully cut joints that distributed loads throughout the entire structure. The stern post was particularly critical because it would eventually support the massive rudder that gave junks their legendary maneuverability. Getting these angles wrong would result in a ship that couldn't steer properly, no matter how well everything else was built. But here's where Chinese shipbuilding really started to show its genius: the planking process. While European ships were built with planks that simply overlapped or butted against each other, junk planks were joined using a combination of mortise and tenon joints, wooden tree nails, and iron spikes that created a hull so tight it was almost like a single piece of carved wood. The edge joining of strakes, the long planks that formed the hull, was an art form in itself. Each plank edge was carefully shaped to fit its neighbour with tolerances measured in fractions of an inch. The mortise and tenon joints weren't just decorative. They actually locked the planks together mechanically, preventing them from separating even under extreme stress. Tree nails driven through these joints expanded when wet, creating connections that got tighter over time rather than looser. When the natural curve of the timber wasn't sufficient for the hull shape, The Chinese had perfected steam-bending techniques that could coax even stubborn hardwood into the required curves. The steam-bending pit was essentially a wooden sauna for ship timber. Planks were exposed to pressurized steam until the lignin in the wood became pliable, then carefully bent into shape and held with temporary braces until the wood cooled and locked into its new form. The caulking process was where attention to detail could mean the difference between a tight ship and a floating coffin. Chinese shipwrights used oakum, old rope fibers picked apart by hand, but they prepared it in ways that European caulkers never imagined. The oakum was treated with tung oil and mixed with specific types of tree resin that would swell when wet, creating seams that actually got tighter in rough weather. Over this traditional caulking went multiple coats of lacquer made from tung oil, tree saps, and secret additives that varied from shipyard to shipyard. This wasn't just waterproofing. It was a complex chemical system that penetrated the wood fibers and created a protective barrier that could flex with the hull without cracking. The best lacquer masters guarded their formulas like family secrets, and ships finished with superior lacquer work could last decades longer than their competitors. The most revolutionary aspect of junk construction was yet to come: the watertight bulkheads that would make these ships virtually unsinkable. Unlike European ships, which were essentially hollow shells that would flood completely if breached, junks were divided into separate compartments by solid transverse bulkheads that ran from the keel to well above the waterline. These weren't flimsy partitions. They were structural elements that actually strengthened the hull while providing the watertight integrity that made junks so legendary. Each bulkhead was constructed like a miniature wall, with heavy timber framing and tight-fitted planking that was caulked and sealed just as carefully as the outer hull. The result was a ship that could lose 1, 2, or even 3 compartments to damage and still remain afloat and operational. The genius of this system became obvious the first time you saw a junk take battle damage. European ships that suffered hull breaches would start taking on water throughout their entire length. The crew would be racing against time to plug holes while the ship gradually settled deeper into the water. But when a junk got hit, the damaged compartment would flood, and that was it. The rest of the ship stayed bone dry, and you could actually sail home with 1 or more compartments completely flooded. Here's what really blew my mind when I learned about this. The Chinese were using watertight bulkheads in the 2nd century AD. That's right. They had this technology for over 1,000 years before European shipbuilders even started experimenting with it. And it wasn't just about surviving damage. These compartments served multiple purposes that made the ships incredibly versatile. Different compartments could hold different types of cargo, each one sealed from the others. You could carry water in one section, grain in another, and valuable porcelain in a third, all without worrying about contamination between loads. Some compartments were specifically designed as ballast tanks. They could be flooded or emptied to adjust the ship's trim for different loading conditions or weather. It was like having a ship that could redesign itself for each voyage. The construction of these bulkheads required incredible precision. Each one had to fit perfectly against the hull curves while maintaining its structural integrity. The master builders developed templates and patterns that ensured every bulkhead would match the ship's lines exactly. The joints where the bulkheads met the hull were sealed with multiple layers of caulking and lacquer, creating connections that were actually stronger than the surrounding wood. But building a watertight hull was pointless without a proper deck structure to keep everything together. The deck and superstructure of a Ming junk was where functionality met craftsmanship in ways that would make modern yacht builders jealous. The main deck beams weren't just laid across the hull, they were integrated into the bulkhead system, creating a framework that tied the entire ship together into one incredibly strong unit. These beams were massive pieces of timber, often requiring teams of workers just to lift them into position. Between the main beams, smaller pieces called carlings provided additional support and helped distribute loads across the entire deck structure. The deck planking itself was another showcase of Chinese joinery techniques. Each plank was carefully fitted to its neighbours with tongue and groove joints that prevented water from seeping through while allowing the wood to expand and contract with changing humidity. The surface was left slightly rough to provide grip for crew members working in wet conditions, a practical detail that showed how much thought went into every aspect of the ship's design. The raised forecastle and sterncastle weren't just decorative additions. They were carefully engineered structures that served multiple critical functions. The forecastle provided elevated space for handling the massive anchors and managing the complex rigging systems that controlled the sails. The sterncastle housed the steering gear and provided protected space for navigation equipment and the ship's officers. These raised structures also served as fighting platforms when necessary. Pirates were a constant threat in many Asian waters, and junk designers made sure their ships could defend themselves effectively. The elevated positions gave defenders clear fields of fire while providing some protection from attackers trying to board from smaller vessels. Water management was built into every aspect of the deck design. Scuppers, drainage holes along the sides, were positioned to quickly shed water that came aboard during rough weather. Freeing ports allowed larger volumes of water to escape quickly if waves broke over the deck. The entire system was designed so that no matter how much water came aboard, it would find its way back to the sea within minutes. Now we come to one of the most distinctive features of any Chinese junk: the rudder system that gave these ships their legendary maneuverability. While European ships were still using simple tillers that required enormous strength to operate in heavy weather, Chinese shipbuilders had developed balanced rudders that could be controlled by a single person, even in the worst conditions. The rudder itself was a massive piece of engineering. On a large junk, it might extend 10 feet below the keel and stand 8 feet above the waterline. This wasn't just a flatboard stuck in the water. It was a carefully shaped hydrofoil designed to provide maximum steering effect with minimum effort. The balance came from extending part of the rudder forward of its pivot point, so water pressure would help rather than fight the helmsman's efforts. The mounting system was equally sophisticated. Instead of hanging the rudder from simple hinges, Chinese shipbuilders used a system of pintleys and gudgeons that allowed the massive rudder to be raised or lowered as needed. In shallow water, the rudder could be lifted to prevent grounding. In deep water, it could be lowered to its full depth for maximum steering power. The steering tackle connected the rudder to a deck-mounted drum that allowed precise control with mechanical advantage. Multiple crew members could operate the system in heavy weather, or a single helmsman could handle normal sailing conditions. Emergency steering systems provided backup control in case the main tackle was damaged, a level of redundancy that showed just how thoroughly Chinese designers thought through every possible failure mode. But even the most maneuverable ship is useless without an efficient propulsion system. And this is where Chinese sail technology really showed its superiority over Western designs. The distinctive battened lug sails that made junks instantly recognizable weren't just aesthetically different. They represented centuries of evolution toward the most practical sailing system ever developed. The sail loft was where master sailmakers worked with materials and techniques that European sailmakers wouldn't discover for centuries. The sails themselves were cut from panels of canvas or matting, but the real innovation was in the batten system that gave the sails their characteristic appearance and incredible functionality. The battens weren't just decorative strips, they were structural elements made from carefully selected bamboo that transformed each sail into a semi-rigid airfoil. When properly set, a battened sail maintained its shape much better than Western sails, providing more consistent power and better performance in varying wind conditions. The battens also allowed the sail to be reefed, reduced in size during strong winds, much more easily than traditional sails. Here's what made this system truly revolutionary. You could adjust each individual panel of the sail independently. If the wind was stronger at the top of the mast, you could reduce just the upper panels while leaving the lower ones fully set. If you needed to balance the ship differently, you could adjust the forward or after panels separately. It was like having a sail system with dozens of built-in configurations. The sheets and reef points were arranged so that major sail adjustments could be made quickly by a small crew. European ships often required dozens of men to reef their sails in heavy weather, but a junk's battened sails could be shortened by just 2 or 3 skilled sailors working together. In a sudden squall, this difference could mean the difference between riding out the storm safely or losing the mast to excessive wind pressure. The mast stepping process showed the same attention to practical detail that characterized every aspect of junk construction. The masts weren't just stuck through holes in the deck, they were carefully engineered to distribute their loads throughout the ship's structure while allowing for easy removal and replacement when necessary. The mast system revealed another layer of Chinese engineering brilliance that most people never think about. Each mast sat in a tabernacle, a wooden housing that allowed the entire spar to be lowered flat on deck when needed. This wasn't just convenient for passing under bridges, it was a survival feature that could save your ship in a typhoon. When European sailors faced impossible weather, they had 2 choices: ride it out and pray, or lose their masts to the wind. Chinese crews had a third option: drop the masts, batten down everything, and let the storm pass over their low-profile hull. The mast partners, the structural framework that supported each mast where it passed through the deck, were engineered like miniature buildings. Heavy timbers distributed the enormous compression loads from the sail pressure down through the deck beams and into the hull structure below. The fit was so precise that the masts could flex and work in heavy seas without creating leaks or structural damage. But what really set these rigs apart was how everything worked together as a system. The balanced rudder, the compartmentalized hull, and the flexible sail plan created a vessel that could handle conditions that would destroy other ships. A junk could literally sail through a typhoon by progressively reducing sail area, sealing off any damaged compartments, and using its deep rudder to maintain control even in mountainous seas. The ground tackle system showed the same practical thinking that went into every other aspect of these ships. Chinese anchors weren't just hooks thrown overboard, they were carefully designed tools that could hold a massive ship in any type of bottom conditions. The anchors themselves were works of art, with flukes shaped to bite into mud, sand, or rocky bottoms with equal effectiveness. The anchor cable wasn't rope as Europeans knew it, but specially laid hemp cordage that could stretch under load without breaking. This elasticity was crucial because it allowed the ship to ride out storms without snapping the cable or dragging the anchor. The Chinese had calculated the exact amount of stretch needed for different weather conditions and sized their cables accordingly. The windlass and capstan systems for handling these massive anchors required their own engineering solutions. A large junk's main anchor might weigh over 1,000 pounds, and raising it from deep water required mechanical advantage that human muscle alone couldn't provide. The capstans were massive wooden drums with long bars that allowed teams of men to multiply their strength. But the real cleverness was in the pawel and ratchet systems that prevented the anchor from running back out if someone lost their grip. The bow arrangement included specialized chocks and fairleads that guided the anchor cable without chafing or jamming. These weren't just holes cut in the bulwarks. They were carefully shaped openings lined with hardwood or even bronze to handle the enormous loads without damage. The positioning was calculated so the anchor would deploy cleanly even in rough seas, and the recovery angle would help break the anchor out of the bottom when it was time to sail. For ships operating in pirate-infested waters, armament became another consideration in the construction process. Swivel guns were mounted on reinforced sections of the bulwarks, with the mounting points engineered to handle the shock of firing without damaging the ship's structure. The elevated fighting platforms weren't just places to stand, they were designed to give defenders maximum advantage while protecting the ship's vital equipment. The pump wells and bilge systems revealed yet another layer of practical engineering. Even with watertight compartments, Any ship would take on some water through normal wear and the constant working of the hull in seaway. Chinese shipbuilders created bilge systems that could handle water from multiple compartments simultaneously, with pumps that could be operated by small crews even in rough weather. The pump design itself was ingenious. A series of leather valves and wooden pistons that could move large volumes of water with relatively little effort. The pump handles were positioned so they could be operated from protected positions, and backup pumps ensured that losing one to damage wouldn't doom the ship. Some vessels even had pumps that could transfer water between compartments, allowing crews to adjust trim or isolate damage without going to the dangerous work of opening compartment doors at sea. Throughout this entire construction process, the human organization was as impressive as the technical achievements. The shipyard operated like a medieval factory, with specialized crews for each aspect of the work. The master builder was like a combination architect, engineer, and project manager, coordinating dozens of specialists while maintaining quality standards that would impress modern manufacturers. Adzemen were the sculptors of the shipyard, shaping massive timbers with tools that seemed too simple for such precise work. These weren't random workers with sharp tools. They were highly skilled craftsmen who could shape a curved hull plank to within a quarter-inch of its final dimensions, using nothing but muscle memory and years of experience. The sound of their work created the rhythm of the shipyard, a constant percussion that meant progress was being made. Caulkers formed their own specialized guild, with techniques passed down through generations of masters. The quality of their work could determine whether a ship lasted 5 years or 50, and the best caulkers commanded wages that rivaled the master builders themselves. They worked with materials and methods that were closely guarded secrets, applying their skills with an attention to detail that bordered on obsession. The lacquering crews were the chemists of the operation, mixing compounds that would protect the ship's wood from everything the ocean could throw at it. Their workshops were filled with bubbling pots and drying racks, where multiple coats of different formulations were applied in carefully timed sequences. The smell of their work permeated the entire shipyard, a complex mixture of oils, resins, and organic compounds that somehow combined to create coatings more durable than anything Europeans had developed. Sailmakers worked in their own specialized lofts, cutting and sewing the massive panels that would power these vessels across thousands of miles of ocean. Their work required not just skill with needle and thread, but understanding of aerodynamics and structural engineering. A poorly cut sail could make the difference between a successful voyage and a disaster at sea. Rope makers operated their walks, long, straight buildings where hemp fibers were twisted into cordage strong enough to control these massive ships. The rope for a single large junk represented months of work by skilled craftsmen, with different types of cordage for running rigging, standing rigging, and anchor cables. Each type required different materials and techniques, all of which had been perfected through centuries of trial and error. The quality control system would have impressed modern manufacturers. Imperial inspectors made regular visits to ensure that materials and workmanship met established standards. Ships built for government service underwent inspections so thorough that every joint, every piece of hardware, and every section of caulking was examined and approved before the vessel could be accepted. Payment systems reflected the importance of quality work. Master craftsmen received not just wages, but shares in successful voyages, giving them direct incentive to build ships that would survive and prosper. Guild rules governed everything from apprentice training to retirement benefits, creating a system that attracted and retained the best talent available. The final phases of construction brought together all these specialized skills in a crescendo of coordinated activity that would culminate in one of the most important moments in any ship's life: the launch ceremony that would determine whether months of careful work would float or sink. Launch day at a Ming shipyard wasn't just about getting a ship into the water. It was a carefully orchestrated event that combined engineering precision with spiritual ritual. The master builder would spend days checking and rechecking every detail, because once that massive hull started sliding down the greased skids, There was no stopping it. One miscalculation could send months of work crashing sideways into the tidal creek, or worse, sliding backward into the workers who'd spent their lives building it. The skids themselves were engineering marvels in their own right. These weren't just logs thrown under the hull. They were carefully shaped timbers positioned at precise angles to guide the ship's descent into the water. The grease came from a mixture of animal fat, tallow, and sometimes whale oil when it was available. Getting the consistency right was crucial. Too thick and the ship might stick halfway down. Too thin and it might accelerate beyond control. But before any of that technical preparation began, there were the offerings to Mazu, the sea goddess who protected sailors and their vessels. These weren't token gestures. They were elaborate ceremonies involving incense, food offerings, and prayers that could last for hours. The workers genuinely believed that launching a ship without proper spiritual preparation was asking for disaster, and given how many things could go wrong at sea, they weren't taking any chances. The actual launch sequence was like watching controlled chaos orchestrated by someone who knew exactly what they were doing. Teams of workers would position themselves along the hull with long poles and ropes, ready to guide the ship's movement and prevent it from veering off course. The master builder would make one final inspection, checking that all the temporary supports were properly positioned and that the launching cradle was secure. When everything was ready, the signal would come, usually a horn blast that could be heard throughout the shipyard. Workers would begin knocking away the blocks that held the ship in place, starting from the stern and working forward in a carefully timed sequence. The first movement was almost imperceptible, just a slight settling as the weight transferred from the building blocks to the launching skids. Then came the moment that made everyone hold their breath. The ship would start to move. Slowly at first, just inches, but building momentum as gravity took over. The sound was incredible. The groaning of stressed timbers, the scraping of the hull against the skids, and the shouting of workers coordinating their efforts. A large junk could weigh over 800 tons when empty, and watching that much mass slide toward the water was both thrilling and terrifying. The splash at the end was the moment of truth. If the ship hit the water cleanly and settled to its designed waterline, the cheers would echo across the entire shipyard. But launches could go wrong in spectacular ways. Ships had been known to stick on the skids, requiring days of work to free them. Others had hit the water at the wrong angle and nearly capsized before they could be stabilized. Once safely afloat, the real work began again. The newly launched hull would be towed to the outfitting quay, where it would spend weeks being transformed from an empty shell into a fully functional vessel. This phase was like watching a house being furnished, except the house was floating and everything had to be secured against the motion of the sea. The rigging process alone was a masterpiece of coordination. The masts had to be stepped with millimeter precision, too far forward or aft, and the ship would never balance properly under sail. Teams of riggers would install the complex web of lines that controlled the sails, each rope carefully positioned and tensioned according to formulas that had been refined over centuries. The sail-bending process was where the battened lug sail system really showed its sophistication. Each sail was custom-fitted to its mast and boom, with the bamboo battens spaced according to calculations that took into account the mast's flexibility, the expected wind loads, and the sail's position in the overall rig. Getting this wrong could result in sails that wouldn't set properly, or worse, rigging that would fail in the first strong breeze. Meanwhile, other crews were loading the essential stores that would keep the ship operational during its voyages. Fresh water casks had to be positioned to maintain proper trim while remaining accessible to the crew. The placement wasn't random. Water was heavy, and putting it in the wrong location could affect how the ship sailed or even make it unstable in rough weather. The compass installation required its own specialized knowledge. Chinese magnetic compasses were sophisticated instruments, but they had to be positioned away from the ship's iron fittings to avoid magnetic interference. The compass house was usually built of non-ferrous materials and positioned where the navigator could easily access it while remaining protected from weather. Ballast loading was perhaps the most critical part of the outfitting process. Too little ballast, and the ship would be tender, likely to capsize in strong winds. Too much, and it would be sluggish and slow. The ballast had to be distributed to achieve the proper trim, with the chine, the transition between the hull bottom and sides, at exactly the right angle to the waterline for optimal performance. The master builders had developed rules of thumb for ballast placement that seemed almost magical in their precision. They could look at a newly launched hull and tell you exactly how many tons of stone needed to go in which compartment to achieve the perfect sailing trim. This knowledge came from generations of experience, with successful formulas jealously guarded and passed down through shipyard dynasties. Navigation equipment installation revealed another layer of Chinese maritime sophistication. Beyond the compass, ships carried star charts, pilot books, and specialized instruments for celestial navigation that rivaled anything used in the West. The pilot books were particularly impressive. Detailed guides that described currents, seasonal wind patterns, safe anchorages, and hazards along specific routes. These navigation aids weren't just academic exercises. Chinese navigators had mapped trade routes that stretched from Southeast Asia to the Indian Ocean and beyond, with timing charts that showed exactly when to catch favorable monsoons for different destinations. A skilled navigator could plan a round trip that might take 18 months, timing each leg to take advantage of seasonal weather patterns. But all the careful construction and outfitting in the world meant nothing if the ship couldn't survive the harsh realities of ocean voyaging. This is where the true genius of junk design became apparent, not just in how they were built, but in how they were maintained and repaired during long voyages far from any shipyard. The modular nature of junk construction made at-sea repairs not just possible, but relatively straightforward. When a European ship suffered structural damage, the repairs often required specialized tools and materials that weren't available at sea. But junk construction techniques were designed around the assumption that major repairs might be needed anywhere, anytime. The watertight compartment system meant that even serious hull damage didn't necessarily spell doom. Crews carried spare planking, oakum, and lacquering materials as standard equipment. If a compartment was holed, it could be sealed off and repaired from the inside while the ship remained operational. Some damaged junks actually sailed for weeks with entire compartments flooded, completing their voyages before undertaking permanent repairs. Storm damage control was built into the ship's DNA. The battened sail system meant that sails could be quickly reduced or completely struck without requiring crews to work aloft in dangerous conditions. The ability to lower the masts entirely meant that even the most severe weather could be weathered by presenting minimal windage to the storm. Worm and rot control was an ongoing battle that required constant vigilance. The lacquer systems helped, but they weren't perfect. Crews carried materials for touching up the protective coatings, and regular inspections below the waterline were part of normal operations. Some ships carried copper or bronze sheathing materials for emergency patches over areas where shipworms had gained a foothold. The rope and rigging systems were designed for easy replacement and repair. Chinese rope-making techniques produced cordage that could be spliced and mended at sea using tools and materials that every ship carried as standard equipment. The battened sail system meant that damaged sail panels could be replaced individually without requiring an entirely new sail. Perhaps most impressively, the ships were designed so that most maintenance could be performed by the regular crew using basic tools. While European ships often required specialized shipwrights for major repairs, junk construction techniques were simple enough that any competent sailor could perform most necessary work. This wasn't just convenient. It was essential for ships that might spend months away from any port with proper facilities. The success of this entire system, the sophisticated construction techniques, the practical design features, and the maintainable engineering, created something remarkable in maritime history. For over 1,000 years, Chinese junks dominated the seas of Asia, not through military conquest, but through sheer practical superiority. These vessels could carry more cargo farther and more safely than any competing design. They could survive damage that would sink other ships, operate with smaller crews, and be repaired using materials and techniques available almost anywhere. The combination of watertight bulkheads, flexible rigging, and robust construction created vessels that were genuinely superior to anything else on the water. The economic impact was staggering. Trade routes that had been limited by the capabilities of earlier ships suddenly became reliable commercial highways. Merchants could plan voyages with confidence, knowing their ships could handle whatever weather or accidents might arise. The reduced crew requirements meant lower operating costs, while the increased cargo capacity meant higher profits. But perhaps the most impressive aspect of the junk design wasn't its individual innovations. It was how all these elements worked together as a complete system. The watertight compartments, the battened sails, the balanced rudders, the modular construction. Each element made the others more effective, creating vessels that were genuinely greater than the sum of their parts. And that's the real story behind those strange-looking ships with the funny sails. When European explorers first encountered Chinese junks in the 16th century, they weren't just looking at different boats, they were witnessing centuries of accumulated maritime genius that had solved problems Western shipbuilders didn't even know existed. The watertight bulkheads, the battened sail systems, the balanced rudders, and the modular construction techniques weren't just clever innovations. They were the foundation of a maritime empire that connected half the world through trade and exploration. The next time you see a picture of a Chinese junk, remember, you're looking at one of humanity's greatest engineering achievements, built by craftsmen who understood that survival at sea required more than just floating. It required thinking 3 storms ahead.